In the last module, we had derived the integral energy equation on the lines of the integral momentum equation that were derived in the earlier module. The final form of the integral energy equation looks like this. We said that each of these terms were non-dimensional. It is an ordinary differential equation for the enthalpy thickness, and there are several terms. This is the rate of growth of the enthalpy thickness along the flow direction, d delta 2 by dx. This needs to be retained. This term is because of the variation in the free stream velocity. If you go back to your momentum equation, boundary layer momentum equation, there was a term for the pressure. So, in the boundary layer equation, this would have been shown to you in the earlier module. So, rho u infinity du infinity by dx is nothing but minus dp by dx. This was the term, okay, because we look at the pressure, we would, if we look at the momentum equation in the free stream, you will get that dp by dy is identically equal to 0, so on and so forth, and that is why dp by dx would translate to this u infinity by du infinity x. So, this term represents the pressure gradient, dp by dx term. It appears as a gradient of the velocity. This term is the wall temperature variation, straightforward, directly. This term, which is suction or blowing, where you are having a velocity from the wall either into the plate or into the geometry, or velocity of the fluid being taken out. This term is your viscous dissipation term. So, this is a very general expression which relates the heat transfer coefficient, which is a Stanton number, to the rate of growth of the enthalpy thickness along the flow direction. For the most general case of varying free stream velocity or imposed pressure gradient, varying wall temperature with suction or blowing, and viscous dissipation. Now, to solve this is beyond the scope of an undergraduate class. So, what is done is we make simplifying assumptions. So, this is the equation. If I have for flow over a flat plate, u infinity is constant, pressure gradient is 0, this will drop off. Constant wall temperature, this will drop off. No suction or blowing, this will drop off. Neglecting viscous dissipation, which is important only for high speed flows, this will also drop off. So, if I list the assumptions here, we have 4 assumptions, that is flow over a flat plate, u infinity is constant, that means du infinity by dx is equal to 0. This is the first assumption. Second assumption, no suction or blowing. This means Vw equal to 0. Third assumption, viscous dissipation neglected, implies 2 nu Eckert number by u infinity cubed by, times this is small, it can be neglected. Wall temperature constant, therefore, d by dx of T wall minus T infinity is 0. Therefore, integrated energy equation becomes d delta 2 by dx is equal to local Stanton number. After dropping all the other terms, this is my simplified integrated energy equation. So, let us consider the case for Prandtl number approximately equal to 1. That means delta is of the same order as delta t. okay, and a third order polynomial profile where theta is equal to t minus t infinity divided by t wall minus t infinity a plus b eta t plus c eta t squared plus d eta t cubed, where eta t is nothing but y over delta t, which is a function of x. In this case, delta t and delta are almost the same, so it can be y over delta as we did in the previous definition. Remember, we had this solution u over u infinity is 3 by 2 eta minus half eta cube. This was derived in a module, I think 2 modules ago, derived earlier, right. So, we will do something similar. So, this is my non-dimensional temperature distribution, and if this is the non-dimensional temperature profile, I need 4 boundary conditions to evaluate the 4 coefficients A, B, C and D. So, what are the boundary conditions? Let us now consider the following. This could be delta or delta t, it does not matter. In this case, y is this way, x is this way, this is T wall, this is T infinity, and here is my temperature profile, which is T of x comma y. Delta t is a function of x. So, BCs. First one, at y equal to 0, which means eta t equal to 0, eta t is nothing but y over delta, t is equal to T wall, which means theta equal to 1 because t equal to T wall, correct. Second boundary condition, at y equal to delta t, which means eta t equal to 1, t is equal to T infinity or theta equal to 0, free stream temperature, so non-dimensional temperature is 0. Third boundary condition is at y equal to delta t. Here we are saying the slope of the temperature profile dt by dy is equal to 0, or this has to be translated. So, this will retain as it is. And the fourth boundary condition, at y equal to 0, we apply or we evaluate the energy equation at y equal to 0, at y equal to 0. What does that mean? I would write rho Cp u dt by dx plus v dt by dy is equal to alpha d squared t by dy squared plus viscous dissipation term is dropping off. So, this is gone. So, this is not there. This term at y equal to 0, u is equal to 0, v equal to 0 because of no slip, correct. So, left hand side of the energy equation is 0. This implies d squared t by dy squared at y equal to 0 is 0. This is my fourth boundary condition. Third boundary condition, at y equal to delta t, dt by dy equal to 0. This is the other boundary condition. So, 4 boundary conditions are there, and using this I should be able to get the coefficients. What do I do for that? So, I evaluate dt by dy. dt by dy has to be evaluated as d by dy of t infinity plus theta t wall minus t infinity, and this, if you do the maths, dt infinity by dy will be 0, and you change this y by delta t equal to eta t. So, dy is equal to delta t d eta t. Okay, so, this can be converted to, using this relationship, I would write this as 1 over delta t d by d eta t of this one, T wall minus T infinity times theta, which is A plus b eta t plus c eta t squared plus d eta t cubed. Okay. T wall minus T infinity will come out, and therefore, I would get derivative of this, which is nothing but dt by dy is equal to T wall minus T infinity by delta t, and within bracket b plus 2c eta t plus 3d eta t squared. This is my expression. D squared t by dy squared is derivative of this quantity. So, d by dy of dt by dy, which is obtained from here, or this is nothing but 1 over delta t d by d eta t of this expression using the transformation. So, I have one delta t, another delta t. So, this is T wall minus T infinity divided by delta t squared d by d eta t of b plus 2c eta t plus 3d eta t squared, which is nothing but T w minus T infinity by delta t squared. This is 2c plus 6d eta t as it is. So, d squared t by dy squared is obtained, dt by dy has also been obtained. So, I use the third boundary condition. So, BC3 is dt by dy at eta t equal to 1. Substitute dt by dy at eta t equal to 1 is nothing but T wall minus T infinity by delta t b plus 2c plus 3d equal to 0, which means b plus 2c plus 3d equal to 0. BC4, d squared t by dy squared at y equal to 0 is 0. So, substitute y equal to 0, which means eta y equal to 0 means eta t equal to 0, correct, because definition of eta is this, y equal to 0, eta t is 0. So, when eta t is 0, so d squared t by dy squared at eta t equal to 0, substitute here 0, I would get T w minus T infinity by delta t squared. This is going to be 2c plus 0 equal to 0, therefore, c equal to 0. I get one number already. Boundary condition 1 and 2 are yet to be used. Boundary condition 1 is this, correct, theta equal to 1 at y equal to 0. So, what is the condition? Let us write it. So, BC1 I am going to use theta is equal to 1, which is nothing but a plus b eta, which is at evaluated at eta t equal to 0, which implies a equal to 1. So, we got a equal to 1, we got from boundary condition number 4 c equal to 0. So, a equal to 1, c equal to 0. We have an expression for b and d here. So, I need another expression for which I use the second boundary condition. So, BC number 2, theta equal to 0 at y equal to delta t or eta t equal to 1. Therefore, 0 equal to a plus b1 plus c1 squared plus d1 cubed, or a plus b plus c plus d equal to 0. A was 1, substitute a equal to 1 implies b plus c plus d equal to minus 1, correct. So, I have two equations now which have b plus c plus d. Substitute c equal to 0 in both, c equal to 0, I get my two expressions which are nothing but b plus d equal to minus 1, this is first one expression, b plus 3d equal to 0, b plus 3d equal to 0. This is the second equation. When I solve for this, I get b, you can eliminate, minus 2d equal to minus 2d equal to minus 1, therefore d equal to half, b is equal to minus 3 by 2, a equal to 1, c equal to 0. So, a equal to 1 and c equal to 0 was obtained earlier, b and d were obtained here now. Therefore, theta is equal to a plus b eta t plus c eta t squared plus d eta t cubed becomes, I get now an equation which is useful. Theta is equal to 1 minus 3 by 2 eta t plus half eta t. This is my temperature profile. Okay. Not so useful because we still need to get the Stanton number or the Nusselt number. So, what is my integrated energy equation now? Integrated energy equation on simplification was this: d delta 2 by dx equal to Stanton number. So, I need to evaluate d delta 2. So, delta 2 is equal to 0 to infinity u by u infinity t minus t infinity by t wall minus t infinity dy, which is nothing but u over u infinity theta dy going from 0 to infinity. Okay. So, I have u over u infinity from the hydrodynamic solution. U over u infinity from the hydrodynamic solution was 3 by 2. So, u over u infinity is 3 by 2 eta minus half eta cube. Theta is 1 minus 3 by 2 eta t plus half eta t cube. Because Prandtl number is of the order 1, delta is of the order of delta t, implies eta and eta t are identical. Please remember, this is very, very, very important and we are getting a very specific solution, and this requires a little bit of explanation. So, if I take this flat plate and I have delta t like this, delta like this, or I have a flat plate and this is my delta and this is my delta t. Free stream here, it is u infinity, t infinity, u infinity, t infinity. Here it is u infinity because boundary layer ends here. So, if I look at this expression, this is u infinity, t infinity would do this. Here I would have this one, and energy equation has to be solved only in this part. This is T wall here, x and y, this is T wall. Okay. So, what is the thing I want to emphasize here is, whatever be the Prandtl number, the integrand for this, so delta 2 is going to be split. This is what? PR greater than 1. This is PR less than 1. Our case is PR equal to 1. So, when I split this integrand from 0 to infinity, I just call this I. Okay. This is the I. This has to be split from 0 to delta t integrand plus delta t to delta of the integrand plus delta to infinity. This is for PR greater than 1. Beyond this one, u is theta is equal to 0. So, this is 0, theta equal to 0. Here also in this portion, theta is equal to 0 because t equal to t infinity already. So, theta equal to 0 here, enthalpy thickness is 0. So, for Prandtl number greater than 1, delta 2 is sufficient to evaluate between 0 to, this is for Prandtl number greater than 1. For Prandtl number less than 1, for Prandtl number less than 1, I will write this expression this way, Prandtl number less than 1. So, PR less than 1, delta 2 will be evaluated from 0 to delta plus delta to delta t plus delta t to infinity. Delta t to infinity anyway is 0 because theta equal to 0, where c equal to t infinity. In this part, Prandtl number less than 1 case, in this part, second part, u by u infinity is 1 because u is equal to u infinity here. So, my integrand is enthalpy thickness is 0 to delta of u by u infinity theta dy as it is plus theta dy delta to delta t. It is not 0. So, I have two terms here which is for the enthalpy thickness. Okay. So, here I had only one term, this is for Prandtl number less than 1. Prandtl number equal to 1, which is what we are going to do. And where is this useful? Where are all these things useful? I have a case of, in electronic cooling, we have this idea of unheated starting length. That is because the chips are placed slightly away from the edge like this. So, the hydrodynamic boundary layer develops from here, the thermal boundary layer would develop this way. So, this is the case of unheated starting length. Where the thermal boundary layer is going to develop at a location which is away from the starting of the hydrodynamic boundary layer. And mind you, in this case, I should necessarily have the hydrodynamic boundary layer of a greater thickness than the thermal boundary layer, because delta has to be greater than delta t always. I cannot have this delta t crossing this hydrodynamic boundary layer ever. So, this condition of unheated starting length is studied many times in graduate level work. I will just present you the result of it later on. Now, when you have Prandtl number equal to 1 of the order of 1, both the hydrodynamic and the thermal boundary layer are going to be similar in nature, and my enthalpy thickness is going to be obtained just by integration from 0 to delta. So, these is u infinity, t infinity here, this is t wall here. Okay. So, let me write the evaluation of the enthalpy thickness. Delta 2 is now 0 to delta or delta t u by u infinity theta dy. So, this is nothing but, I will write it as 0 to delta or y over delta is equal to eta. So, y equal to 0, eta equal to 0, y equal to delta, eta equal to 1. So, this is 0 to 1, 3 by 2 eta minus half eta cubed, 1 minus 3 by 2 eta is not eta t anymore, plus half eta cubed d eta into delta. Okay. This is the integration. So, once I do this maths, I am not going to do this maths. After I do this maths, I would get, you have to expand the bracket here, nothing, you have to expand the bracket, and you would have 5 terms, apply the limits, you would get delta 2 is equal to, 39 by 280 delta. This is just maths, I am leaving this as an exercise, 39 by 280 into delta. So, Stanton number, if we go back to the definition, Stanton number was Hx by rho Cp u infinity, which was nothing but minus k dt by dy at y equal to 0 divided by rho Cp u infinity, and dt by dy we have obtained here, dt by dy we have obtained here Okay. So, when I substitute for dt by dy from the expression that was there before, I would get this as minus k into b divided by delta t rho Cp u infinity. We have derived dt by dy, substituted at y equal to 0, and because c is equal to 0, you would get this form. So, this is nothing but b is 3 by 2 alpha u infinity into delta. This is my Stanton number. So, integrated energy equation, which is d delta 2 by dx is equal to Stanton number, therefore becomes d by dx of 39 by 280 delta is equal to 3 by 2 alpha by u infinity 1 over delta. I multiply and divide by nu. So, this is nothing but 3 by 2 alpha over nu u infinity by nu 1 over delta. So, this can be rearranged, take this delta there. So, this is 39 by 280 1 by 2 d by dx of delta squared, which is nothing but 3 by 2. Nu over alpha is 1 over Prandtl number, nu over u infinity. You do the maths here. So, these are all constants, you cancel a few things exactly the way we did in the hydrodynamic part. You would get delta by x the whole squared is equal to 4.64 Rex. I will write it as delta t by x the whole square also the same, Rex to the minus half, Pr to the minus half. Prandtl number is there, which is of the order 1, and that is why these two thicknesses are the same. And if I substitute for this in terms of the Stanton number, last couple of steps here. So, Nusselt number is equal to Hx by k, which is nothing but Nu is equal to Repr into Stanton x. Rex Prx is nothing but rho u infinity x by mu. This is Pr as it is. Stanton number we had was 3 by 2 alpha by u infinity delta. So, I substitute for delta here. Okay. This is Re as it is. So, I can write this as Nusselt number would come out to be 0.322 Re to the power half Pr to the power 1 half. This is something which you can do with couple of steps of algebra after having obtained this. What is important here to note, I will just say, in your scaling analysis for Prandtl number of the order of 1, you got Nusselt number is going to scale as Re to the power half Pr to the power half. The beauty of integral method is the following: you get this coefficient very easily with a third order polynomial and couple of simple assumptions which anyway did not alter the difficulty of the problem significantly. So, in these modules on integral method, we saw how a simple polynomial profile for velocity or temperature distribution helps us get reasonably accurate coefficients, which was not obtained by scaling method. Integral method is an approximate solution method. Even though equations are exact, I can use a higher order polynomial to get a better accurate coefficient. Nevertheless, this is a very powerful tool that can be employed for a wide range of convective heat transfer problems. Thank you.